What's up, everyone? Today we're going to work on a high school algebra problem that you probably have seen multiple different versions on the internet, and here is what I call the general version of it. So it says let a be some positive real number, like in other words, strictly greater than 0, and also a is not equal to 1. So we're going to solve the following equation: a to the x power plus the quantity a squared to the x power equals the quantity a cubed to the x power for the variable x that is just any real number. Okay, so you probably have seen some other versions such as 2 to the x power plus 4 to the x power equals 8 to the x power, or something like 3 to the x power plus 9 to the x power equals 27 to the x power. Okay, so for this version, the generalized version, before we talk about the solutions, let's pause the video for a bit and think about it yourself. At the same time, don't forget to like and subscribe my channel if you didn't do it yet. And if you think you're going to enjoy this video, don't forget to share it to your friends either. Okay, are you ready for it? So here we go. First, notice that we now have the base a that is, of course, need to be positive in order to make a sense of us doing the next step. Okay, in order to take the log of a. Also, we have to have the condition that a cannot be equal to 1. Otherwise, let's see what happened. If a equals 1, then we will simplify the equation into 1 to the x power, which is equal to 1, plus 1 squared to the x power, which is again equal to 1, equals the right hand side, which is 1 cubed to the x power, which is 1 to the x power, and again is just equal to 1. But then if we simplify it, we get 2 equals 1, which is a contradiction. Therefore, we have to assume that a cannot be equal to 1 either. Good. So now we see why we have the conditions. Let's talk about what we can do in this problem. So since we know that a is a positive real number and not equal to 1, in other words, a to the x power is always equal to some positive number as well. In other words, a to the x power is not equal to 0. Since a is not equal to 0 for all real number x, a to the x power is not equal to 0. So we're now allowed to divide both sides by a to the x power because we're not dividing by 0. So if we do that, we now get a to the x power divided by a to the x power gives us 1 plus the second term. Now remember, when we say a to the second power to the x power here, by the one of the rules in the exponents, we can just take the products of the exponents together, meaning this term here in the middle is equal to a to the 2x power. So if we take the middle term here divided by a to x power, we'll get something like this: a to the 2x power divided by a to the x power. And then for the right hand side, we'll do the same thing. We now have a to the 3x power divided by a to the x power. So as we simplify the second term and the term on the right hand side, we get 1 is still 1, plus now we're going to take the other property, which says if we're taking a division and they have the same base, we can just simply take the difference of the two exponents, meaning we're going to have 2x minus x given we the x power here. So on the right hand side, we will now have a to the 3x minus x power, which is 2x here. Great. So now, what can we do next? So remember, we just said that when we have the product in the exponent, we can rewrite it back as the form above. They are equivalent. So here, we're going to do the following. We're going to break the exponent 2x into 2 times x, and then we're going to put the x inside this time, and then we will take the 2 outside, and of course don't forget we have the base a here. So if we do it this way, we can now do the substitution. Let our term here, a to the x power, be some new variable. Let's call it what should I call it? Let's call it z here. Okay. Then we now do the substitution. We get 1 plus, we see the a to x power, we're going to replace it by z, equals the right hand side, and since we have rewritten this term into the following, we now get the inside that is replaced by z to the second power, meaning we have z squared. So if we now solve for the variable z and then substitute back in, we'll be able to get the solution for x, which is what we're trying to do. So let's move to the right hand side. So we have 1 plus z equals z squared. So we move everything to, well, doesn't matter. We can move the z squared to the left hand side, and then we're going to multiply everything by -1, such that now, be careful, everything, including here. So now we can just use the quadratic formula, because we now have z squared plus minus z minus 1 equals 0, which is a quadratic expression, meaning that the highest term, or the highest degree in this expression is just degree 2. So we can just use the formula to get our answer no matter what variable we have or what coefficients we have. So let's substitute it. So we have negative b, which is this, plus or minus b squared, which gives us 1 squared, and then minus 4ac. Well, a is just 1, and then c is -1 here. Excuse me, here is, my bad. This is actually b here, negative b is. So we have 4 times a times c over 2a. Again, a is a leading coefficient 1 here. So if we check it and simplify it, we will get 1 plus or minus -1 squared is just 1, and then we have minus a negative, which is plus. 4 times 1 times 1 is 4. So we have 1 plus 4, which is 5. And then all over 2. Now, here comes the question. We have 2 answers here, right? Are they both valid? Let's consider back here when we do the assumption, okay? When we think of this expression z, it is representing a to the x power. But what do we know about a to the x power? Well, get back to above. We know that a is positive, so a to the x power is always positive. Meaning, if a to the x power is equal to z and a to the x power is positive, that gives us z has to be always positive. So if we look at our answer here, One of them gives us a positive result, but the other one is giving us a negative result. Of course, 1 plus radical 5 over 2 is positive, so this is valid. But for the other solution, 1 minus radical 5 over 2, that's negative. So that solution is invalid. Therefore, we do not have to include it back into our expression. So the only option that we can have is 1 plus radical 5 over 2. And again, we're not done yet because we need to solve for x, not just for z. So finally, we're going to substitute back in a to the x power equals 1 plus radical 5 over 2. And again, if you pay attention carefully, this is also known as the inverse of golden ratio. I shouldn't write this way. Should be a little bit more careful. The golden ratio, okay, which is the same as 1 over wait, hold on. Am I doing it correctly? No, this is the golden ratio. So right. Anyway, good. So in order to solve for x, we just need to take log base a on both sides, so that we get log base a here and log base a here, so that the base a and the big A here will be cancelled out, and we finally get our general result. X is equal to log base A of the golden ratio, 1 plus radical 5 over 2. And that's it. Wow. It actually took a little bit longer than I expected as well. So yeah, now we know how to find the solution for any base that we have, since we already have the general results for this kind of problem. Okay, so now we can actually check. Suppose we have base equal 2. So now we're saying that if we have 2 to the x power plus 4 to the x power equals 8 to the x power, then our final result for x would be equal to log base 2 of the golden ratio. Now if we replace the base a to some other numbers like 3, then of course we just change the base a right here into base base 3, and so on. That's it. Did you get it right? Pretty cool, huh? All right. So, yep. I'll see you guys next time.